Good afternoon, everyone. Welcome to another session of the Network Seminar Series hosted by the Center for Network Intelligence at the Robert Bosch Center for Psychophysical Systems, IISc. Today's talk is by Professor Neminath Hubballi, and he'll be speaking on traffic dynamics aware probe selection for fault detection in networks. Professor Neminath is an associate professor in the Department of Computer Science and Engineering, IIT Indore. He earned his PhD from IIT Guwahati. He and his research team mainly work on problems related to network security, system security, and fault detection in networks. Prior to joining IIT Indore, he has worked with Hewlett-Packard, Infosys Lab, and Samsung R&D on various projects. He served as TPC co-chair of IEEE ANTS 2018 and designated as TPC chair of IEEE ANTS 2021. He has been awarded a Duo India Fellowship in the year 2020 to visit City University of London for a collaborative research work. He was a visiting researcher at NTNU Norway in 2019. Before we move on to the talk, we'd like to request the audience to subscribe to our Google group for information on future talks. You can also visit our website for more details. I'll be pasting the links in the chat box. Please do check. Finally, we request the audience to keep your microphones on silent for the duration of the talk. And for questions, you may ask Professor Neminath or type them in the chat box and we'll moderate it with him. Over to you, Professor Neminath.
Yeah. Thank you. Thank you for the introduction and inviting me to present our work. Let me see the slide. I hope slides are visible.
Yes.
Yeah. So before I begin, let me acknowledge my collaborators. This is a collaborative work with Dr. Maitreyan Nathu. He's with TRDDC Pune. He was an adjunct faculty at IIT Indore some time back, and also one of my master student at IIT Indore. So the agenda for the day, something like this, will begin with the motivation for the problem, and then we'll see the how do we actually, what exactly is probing, and how do we detect the faults. And then the second topic that I would like to briefly talk about is how do we actually handle the probe station failures themselves, and then finally conclusion at end. So computer networks over the years are growing in size, and the complexity of network management is increasing. So the effective network management is an issue without the downtime and the use. These various events that happen in the network, such as traffic shifts, some of the node failures in the network, and many misconfigurations that often happen, may adversely affect the performance of the network. The moment something happens in the network, any event that happens in the network, and the time at which point you actually notice that, and the recovery time, this time lag between the point at which the failure has happened in the network and the time at which it is rectified. So if it is a longer period of time, then your services might be affected. I mean, the network services might be affected. So how do we actually do an effective network management is a question. So in that sense, you do something and you keep monitoring your network elements all along the way. Every time, and then you go and check whether it is functioning properly or not. That is what is required, so that you can actually, if there is an issue, you can actually figure out that issue and rectify that. So here is a picture. It's a Google data center. So just to show the size of the network, so the scale at which they are, the devices are connected. So this diagram taken. So the regular health monitoring or fault detection is typically done in two ways. One is on the right hand side what is shown, something called as the monitoring. In the monitoring, what you have is a network management system or the network management server is sitting one place, and you collect the health information or the logs generated from each of these network elements. These could be routers, switches, or even the servers for that matter. And then you bring it to a central place, and then you process those logs to find out whether these nodes are functioning properly. And of course, with that goes the single point of the failure. But this is not intrusive. So whatever is going on in the network, you just collect that and then try to process and make out something out of that information. That's why the name passive network monitoring. The other way is something called as the probing, which is of the topic to interest to us. In this, what happens is you identify a set of nodes within the network. Here, in this case, the green colored nodes are the ones which are selected. These are called as the probe stations. And these probe stations send probes, or these are probes or queries to other nodes, and then bring the health information from those nodes. So based on what is the response that you get, the probe station can make out whether the node is actually functioning properly or not. This probe could be as simple as a ping request, so just to know whether that device is up and running, or it could be as complex as you want to monitor the application performance, whether the application up and running, so all that. Whatever custom queries you want to generate, you can do that. But now the question is, how do I choose these nodes in the network? Is there any strategy? That is one question in the first place. And second thing, once I choose some of the nodes, which node is going to actually probe which of the other nodes in the network? So for example, in this case, node N5 is actually probing N1 and N2 with this dotted line. And similarly, node N9 is actually probing this N6 and 7 and N8, and similarly other cases. So the question is now, can we select those probes gently so that they don't cross maximum number of the hops in the network? And so you can come up with all kind of peak strategies. So the motivation for our work is, so in a nutshell, this probing actually has got this advantage of you can send any customized queries. Unlike the monitoring is passive. So if the nodes N2 and N3 do not talk to each other, they do not exchange anything, then you will not get any information regarding the communication between those two to network management system. Unlike that, the active probing techniques can actually send customized queries at regular intervals of time and then get the information. So active probing techniques are good for monitoring. And the question that asked is, these probes are, since they are regularly generated in the network, they might actually compete for its share of the bandwidth, because one test query, if you send particularly complex queries, lot of the response might be quite large. And so this probe induced traffic is actually can compete with the traffic. So in that case, can we select the probes? The question that asked is, select the probes such that they pass through the less congested nodes in the network. So now how do we actually do that? What is the notion of the congestion in the network? Which node is actually having large amount of traffic or passing through that node, or it's busy? So in order to do that, what we do is we view the network as a graph, in fact, a weighted graph. So you do have vertices and its set, and then the weight is assigned to each of the edge. So this weight can be any metric that you can choose. So it could be as simple as, in our experiment, we use the network IO statistics. It could be simply the number of the packets that are flowing along that link, or it could be the share of the bandwidth that is utilized, or it could be the occupancy level at the router queue, or any other metric that you think, or RTT value, or anything that you can actually want to use. That metric you can use and then assign. The general framework is flexible enough to accommodate to any of those metrics. And then some of these probe stations actually send, are the ones which send the probes in the network. So there are many options to choose from which one I am going to used to do that. So precisely what we intend to achieve is we are given a graph, which is a weighted graph with a set of probe stations. We are not dealing with how to select the probe stations in this work. There are some prior works which actually and which nodes are actually good choices for the probe station to become the probe stations. Assuming they are there, we want to do this. There are some probe stations in the network. You want to find an optimal set of probes such that the probe induced traffic actually add to the less congested nodes while satisfying the constraint that every node failure can be detected by at least one probe. So one of the probe stations in that is designated should probe one or the other nodes in the network. That is the constraint. So in order to do that,
but can I ask a question?
Yeah, sure.
So what is the definition of optimality here? Maybe I missed something. Optimal set of probes.
The optimal set of probes means the probes that are selected should pass through. I want every node in the graph should have at least one probe going to that node. And then I just want to have the minimum set of the probes will have got a weight. So for example, if I go from N1 to N2 to N3, N4, so that has got a weight. So I just want to select those minimum set of the combinations, which is going to give you that satisfy that constraint. I want to have every node to be covered by at least one probe, some probe station, but the weight is actually minimal. So that weight is actually notion of the congestion that we are talking about.
Okay. So you're going to formally pose this question, right?
Yeah.
Thank you.
So, remember this, the weights are assigned to the edges in the graph, but we want to avoid the congestion at the node level. So then in order to do that, what we do is actually take the edge basis. If an edge is incident on a vertex, you sum it up. So assuming the edge weights are for the time being the number of the packets that are going in the last some interval time. So that gives you an approximate pretty of how many number of the packets or the bytes that node has actually processed or has gone in the last some window period of time. So we convert this edge weight graph into by the edge weights into a node weight graph. Now I want to explore the possible combinations of the probes. So which node is going to probe which other node in the app. So in order to do that, what do is to begin with, we select something called as the candidate probes. Candidate probes are those probes which are actually possible. In the final set, I have only a combination, a certain combination of the probes, but in the candidate probes, you explore all possible combinations of going. So if you look at this diagram, I can go to node N7, N1, N2, N3, N4, N7 as well, N1, N2, N5, N6, and N7. And similarly, there's other combination N1, N2, N3, N6, and N7. So these are possible combinations. This we call it as the candidate probe set. So the candidate probe set can be of length 1 half distance. You have 2 length and 2 half distance probes. You have up to given in n node graph, you have up to length n-1. So you enumerate all of them, and a subset of that would be your final set of the probe that you want to select, meeting that criteria. So this is actually a NP complete problem. This is actually a weighted set cover problem. So you don't. There are approximation algorithms. So we don't use those approximation algorithms in our work, but instead we actually propose some greedy methods with couple of heuristics incorporated. So let me not go into the details of why this is a complete problem. So there is a reference. If anybody is interested, they can take a look at that. So the first, we introduce a couple of heuristic to all this problem. The first heuristic that we introduce is I don't enumerate all the probes up to length n-1 in the node graph, but I restrict the length of the probe to some positive constant k, where k is significantly smaller than n, the number of the nodes, which is much, much smaller. So if, let's say, I have a graph with 100 nodes, I might restrict to maybe 4 to 5 nodes or something like that. So this goes with an implicit assumption that the probe stations are located in the network such that within the k hops, you should be able to reach out to all other nodes in the group. At least every node is reachable within k hops from the one of the probe stations, not necessarily all of them. So that is the option. So by virtue of that, what we are able to achieve is you actually reduce the number of the possibilities that you got. The total combination probes, candidate probes is substantially reduced. The second trick that we may introduce is, yeah, uh, is there any?
Hi, I have a question.
Yeah, sure.
So I understand from your picture there is a particular source and a destination.
Yeah.
Right. And with respect to that,
Mm.
you are constructing all possible paths and everything. I got that.
Yeah.
But when you are probing, you don't know where the failure can be. It can even be your right next hop itself, the first hop itself, that can be a link failure and all that. So
Yeah,
it
yeah.
it need not even traverse all the way up to the last exit point.
Yeah, yeah,
So
you're right. The idea is once you select a path, so every node you are actually, so when you send the probes, you don't send to only that particular destination. So if I say X, Y, G is the, you also send one probe to G and another probe all along the path to Y also. So
no, what I meant was it has to be a recursive thing. By that I'm saying you send it to the first hop,
yeah.
It works. Then you send it to the second hop. So now 1 and 2 work, 1, 2, 3, like that, so on and on.
Yeah. So this is precisely what is done. So you send,
Okay.
because I want to find out the failures at every node, not necessarily all of them. What I'm saying is, if I select a path A, B, C, D, when I select A, B, C, D as one of probe, it also means that I send one probe to A to B, A to C, and also
Correct.
yeah.
There are some clever, just so that there are some clever
Yeah.
things that bisection and all that. I don't
Yeah.
want to
Yeah.
got it.
So the second assumption that we introduce is, let's again mention that the path taken is always the shortest path. Shortest path in terms of the, it could be anything, again, the number of the hops or the metric that you use. You assign that, and then you run a Dijkstra shortest path algorithm from those proof stations. You will get to the path. So I need not explore the paths which actually I want to go from the A to D. Let's say A to D is node A to D is reachable within the k hops, and then I want to go from A to D with taking the shortest path. So thereby again you bring down the number of the candidate probes that are possible. And once I do that, the candidate probes, you pose this optimization problem. I want to minimize the total cost of the selection. So every probe has got some cost, and Y is a binary vector which indicates that selection, subject to the constraint that every non-probe station B minus PS. PS is a set of probe stations. So that is actually proved by at least one of the probe stations. Vi belongs to nodes of CPJ is indicating the what are all the nodes that are covered if I make that selection of the in CPJ. So this actually we show a greedy algorithm here in this slide. So as usual, the node, you begin with the node weight graph, and then you convert that edge weight graph into node weight graph, and then you have a set of probe stations. So you construct something called as to begin with, the reachability matrix. So this reachability matrix indicates whether the node B is reachable within k hops from the node A. Because I don't want to explore the other possible higher length candidate probes in this environment. So first you find out what are all the other nodes which are reachable within the k hops. So and then subsequently you run that extra shortest path algorithm, and after that you calculate or the assign weight to each of the candidate probe. CPI is a candidate probe. So that is simply the summation of the weights of each of the nodes that are involved in the probe. And subsequently, you initialize what are the nodes that are covered to empty set, and then the probe selected at the beginning is empty, and then you do this greedy selection. As long as the number of every node in the graph is covered, so covered intersection, the node or the vertex set is not equal to V, you keep repeating this. What is that? The candidate probe with the maximum number of the uncovered nodes, but having the minimum weight in the, if I have two alternatives, A, B, C, D, and PQR, PQRS, then I go with that selection in the beginning, which is having the which is having the minimum weight in the, which is actually adding minimum weight to the total selection. So then I also keep updating the number of the covered nodes, and then you keep that selection that you made. At the end of this iteration, you will check the what are the selection you have made. So that is the simple greedy algorithm to do the selection in the arm. The first preference always goes with the that probe which is actually having the which is going to cover the maximum number of the uncovered nodes in the greedy selection. So we actually made a second small adjustment into that. What is that? You actually normalize. Why don't we, instead of giving the weight is first preference to the that probe which is covering the maximum number of the nodes, you whatever the weight is there, you divided that by the number of the nodes it covered, so that so by virtue of that you get some normalized notion of the selection. So you go with whichever is having that ratio as the minimum one, you go with that selection. So per node, uncovered node, what is the total cost that I'm adding into the selection? So rest of the things are actually same in the selection. So again, you begin with the adjacency matrix and then cover the convert that in reachability matrix and so forth. So let's take a look at the one sample graph. This is an 8-node graph. There are two probe stations here, N5 and N7, and these are the weights. Some random numbers are assigned to graph. So if I enumerate the possible cases by taking the length as 3 halves, so this is the number of 14 candidate probes are possible. So N5 to N1 is one probe. Similarly, N5, N1, N2 is another probe, and what is the cost of that selection? So the sum of the node weights is this cost. So by running that algorithm, you get this 14 candidate probe set. So after you get this candidate probe set, now the selection. So in ideal case, in order to get the minimal set of the combinations, is unless you explore all possible subset combinations, you don't get that minimal combination. That is why we are going with the greedy approach. So just wanted to compare on that example graph with the 14 node, 14 candidate probes. So if you explore all possible subset combinations, this is our implementation. So for the combinatorial, the subset selection explore algorithm took around 5.7 seconds, and the minimum cost that you can get along this in this graph is 900. The 900 is the number of packets, and these are the 3 probes that the minimal probe that get selected. So if you use these greedy algorithms, so in terms of the time, it's actually much smaller, but obviously you're not doing better in terms of the cost. So these two are the number for greedy algorithm 1 and 2, 1092 and 71. the read algorithm selected 3 probes, and button algorithm 2 selected 4 probes in the network. We also encountered a special case we working with the graphs. This is one example. Again, I think the same example. So we said that in the beginning we wanted to minimize the or avoid the paths which are actually congested. But if you look at this node number N6, when you combine the weights on the incident edges 30, 15, and this turns out to be 50. So in fact, the algorithms 1 and 2 actually selected a probe which is actually passing through this one, because it is not looking at the individual nodes which are congested, but all along the path, what is the actual cost. So as long as the total path cost is smaller than the other options, it keep that selection in the so just to wanted to explore with other options. So can we have the cost of the probe as the weight of the node which is having the maximum node weight in the graph? In that case, can we avoid that node in the graph, because we wanted to avoid the nodes which are actually sending probes to those nodes which are congested. So just to that we modified little bit that algorithm, the way we assign the weights, which is actually now the weight of candidate probe CPI is the weight of that node which is having the maximum in the graph. So then when I do the selection here in this case, I select that probe PI, which is having the minimum weight, min of the maxes. So every candidate probe has got a weight, which is actually the weight of the node which is having the maximum weight. So among the equal probables, which is having the minimum weight, you take that and then you do that greedy selection. So this is a slight addition. By virtue of that, you are actually able to avoid that those cases which are theoretically at least heavily congested, and that meets our objective we stated in the beginning. So we not evaluate the performance of these algorithms. We performed generated some artificial graphs. So these are some 8 nodes graphs increasing. We started with a graph with 3 nodes, 4 nodes, 5 nodes, and we actually increase the number of the edges in that graph, make it little denser, so that you get the number of the candidates probes keep increased. As the number of the edges in the graph, their graph becomes denser, you have more number of the candidate probes. So the more number of the candidate probes you have, the more options you have got for selection. So you need to do more work to do the selection. So we just compared the execution time up to the starting from the 8 candidate probe to 17 probes. So this is, I think, an obvious action. So the combinatorial, the best possible approach would take around 2 minutes to complete for 17 candidate probes, but the greedy approaches did much better within less than second time. So the second set of experiment that we did is using NS3 simulations. We created a topology which is looking like this, and then we scheduled some of the flows between the nodes in the graph. So the details of are not which flows from which node to which node are not shown here, but what is the number on the edges indicate the number of the packets that are flowing through that edge in the last window period. We took 10 minutes as the window period. So that's also again indicated with the thickness around the edges. So this is the number of the packet that flew traverse between node N4 and N14, and similarly for the other nodes. And then we change the number of the flows between the nodes, we that, and then you get in the next 10 minutes, you get a different kind of graph with a different set of weights. And in the third interval time, again, you have different set of flows and different set of flows. By virtue of that, you actually again have the different set of weights assigned to the edges in the graph. Now, using these graphs, we actually wanted to explore. So, because we want to change the probes that are selected in response to the dynamics that is happening in the network. So, do that, you profile in the last window period what is the condition in the network, and then you keep changing the probes that are that is the selection that you make. So, what is the optimal Dury window period, and how do I actually go make sure that this is the window period that is correct? That is actually answered, which I am not going to cover in this talk. But assuming that is there, this is the so this table is actually showing the flows that are scheduled. So this in the first 10 minutes, the flows F1 between node N1 and N4, N11 to N12, and so forth. And the algorithm one, what is the selection that it made, the final probes that are selected, and the time it took to do that selection, and the total cost, that is the cost of that selection. And similarly goes for the other two algorithms as well, with the 2 and 3. And their costs and the selection that they made are also shown here. And subsequently, when you go change the flows, of course, the weights on the edges also change, and the network graph also change, and then you get a different set of the selection. Similarly, for the 20 to 30 minutes, also you have different set of selection. So their weights are actually shown here. So the point is, when you have the variation, the dynamics in the network changes, something happens, then you have a different set of probes which are coming, and then meeting that criteria. Every you make an attempt, unless there is a partition in the graph, you actually go explore other possible paths and then try to make sure that the nodes are actually proved by the other partitions. And that was a toy example, just to make to show that the things that we wanted to happen are indeed happening. So we actually move on to look some graphs taken from the Internet Service Provider Network. So these are actually the large graphs. There is a project, Rocketfuel Project. This is a slightly old project. They built the topology of the internet by generating some trace route queries from different points in the network, and then build the topology of the network. Those are identified by autonomous system number. So what is shown here is the autonomous. We took some of those graphs. These are the number of the nodes in that graph and the number of the edges in that graph, and the candidate probes that are selected generated from that graph, assuming the length of the probe is restricted to 4 hops, and the number of the probe stations are in some of the graphs except one, it is the number of the probe stations in that graph. In all of them, remaining 5 of them are 6 nodes in the graph. And then the these are unweighted graphs. There is no notion, just it shows the topology, nothing on that. We assigned some random numbers in between some lower and maximum to each of the edges in that graph, and then generated the weighted graph, converted those unweighted graphs into weighted graphs, and then ran the algorithm 1 and 3. This is the cost of selection and the time selection for different algorithms for different system numbers. So again, you can see that actually algorithm 1 and 2 are doing more or less similar kind of selection, but since the other third algorithm, it's not very consistent. What observed is whether the cost is going to be always higher or the lower, but it appears that the number on an average the cost of the selection with the algorithm 3 is slightly higher. So after that, we also compared the performance with another approach. This is just to study if I disregard the weight notion of the weight in the selection. So assuming I just go with the random selection in the graph, I keep adding the probes, which only selecting those probes which are covering the maximum number of the nodes, of course, within the length k. And then you compare the performance of that with the greedy selection that you are doing. So in terms of the cost, how do you do? In terms of the number of the probe selection, how do you do? In terms of the time, how do you do compared? I'm not sure whether these writings on the top is visible. So the lines are not in fact consistent. That is what I noticed recently. If I can go over this one, the cost of this comparison with the yellow line at the top is, if you do a random selection, that's going to give you, as usual, the highest cost, because I'm not taking the cost into account. And all of these greedy algorithms are actually doing better in terms of the cost. But if you do the same thing, compare with the number of the probes, the random approach, the random selection has got the maximum number of the probes. The purple color line again at the top is actually showing that, and the three greedy algorithms are below that. So in terms of the cost and the number of the probes, these algorithms are doing better. And in terms of the time, not sure what is this. Okay, whether we are doing better or yeah, you can keep it as they are comparable. So subsequent to that, we studied a couple of properties of these greedy algorithms. So if I make use of these greedy algorithms, what is exactly going to happen? So if I given a node weight graph, the selection use the good algorithms, the property that holds good is any two proofs that you select in graph will have at least one edge is common. We make an assumption that the graph is simple. There are no parallel edges and the self loops in the graph. So without going into the details of the proof, there's what to say. There are no proofs which are actually completely overlapping. For example, node N1 to N6, you select a probe and subsequently you don't go other way around to the selection. These are not required in the graph. So that property holds good. And as a consequence of that one, so if the graph is simple, and if every selection is going to involve at least one edge which is not selected previously, then at least one new node is actually proved by that selection. So as a consequence of that, the number of what is the upper bound, what is the largest number of the probes that I'm going to have in the network turns out to be 1 minus the number of the nodes that you have in the graph. This is a theoretical upper bound, but it need not be that. The moment you have more than one hop distance probe, then by only definition of that selection, you will have the ABC. So B and B is also, if I make that selection ABC, A to B is already by default covered. So we will have lesser number of the probes in the final selection. But in sense, if you think of the cases, you have a probe station sitting at the center and all other nodes are just the one half distance. You have a hub and spoke model. So that's the worst case scenario that you can see.
I have a question.
Yeah, sure.
So how we are defining cost? Is it number of hops or is it link characteristics like bandwidth? And
you can use any metric that is suitable for you. So it can be number of the hops, it can be number of the packets flowing through that link. It could be even the RTT values, whatever you think, what metric you think. So as long as you are able to assign some weight to the each of the links, then the selection is going to be valid. So it doesn't.
Okay. So in one case where we take this cost as a dynamic parameter, for example, latency or bandwidth,
Yeah.
that will keep on changing if the network is active and traffic is going. So will these algorithms have to recalculate the number of probe packets and
Yeah. So actually, the way to deal with that is you are right. The RTT value or the things will keep changing. So I don't want to rerun the algorithm. So every now and then, you can set certain parameters like only when the changes are beyond certain threshold, I'm going to rerun the redo the reselection of the probes in the network. And when I send the probes, I can be reactive to those changes. So, for example, if I take the RTT as a metric for selection, when I send the query to the node and then I get back the answer, based on that, if let's say the RTT value increases, then roughly I can assume that there is an increased congestion all along the path somewhere, I don't know. So then I can reduce the frequency with which I can actually send those queries. And thereby, for the short-term reaction dynamics in the network, you control the adjust the probe frequency and then deal with that. But only when the changes are too large, then you do rerun those algorithms and then do the selection again.
so the results that you showed in previous slide. So have this criteria is considered in?
No, these are not considered. These are just the plain way. In fact, the Rocketfuel experiment that I showed is actually these are not weighted graphs. These are unweighted graphs. Just the topology is given. We assigned some numbers to random numbers to each of the edges and converted them into weighted graphs and then ran the algorithm.
So it's kind of a network with static weights.
Yeah, this is whatever is shown here is the static weight. We did another set of experiments experimentally in the internet for a longer period, to some of the servers on the internet and then did the measurement study. So that is not there here in this set of the results. So those are there. What you're saying is right.
Okay. Thank you, Professor.
Yeah. So the second question that we is what if we designated some of the nodes as the probe stations? So these probe stations are also the nodes, like any other node in the network. What if those probe stations themselves fail? Can we build some fault tolerant model? So the simple answer is make one probe station probe the other probe stations. So one node, if P1 and P2 are probe stations, P1 probes P2 and P2 probes P1. And then if one of the probe station fails in the network, then you reassign the responsibility of probing the other nodes. So initially, when whatever the probes that probe station P1 is probing, you could redelegate to some of the other probes, whatever the probe stations that are remaining, you reassign them and then you continue the health monitoring operation. So that's what you are given again in node weight graph, and we are having some probe stations. You want to do the optimal selection such that every node in the graph, non-probe station node is at least probed by at least one of the probe station. And also additional constraint, every probe station is also probed by other probe stations, where PSI and PSJ are two probe stations. They are distinct. So the optimization problem some slightly changes with an additional constraint. Again, every candidate probe has got a weight, and then for every non-probe station, V minus Vs, there exists one probe which actually probe that. And for every probe station, P belonging to the set PS, there is another probe, which is prober of P is not equal to P. So prober of P is the other probe station. That it itself is not probing. That is the. And then you do again the greedy selection. So you select in each iteration the candidate probes. Now only the weight assignment is also slightly changed. So it is the weight of the nodes other than the probe station node plus the add probe station weight, which is actually probing that node. And then again do the greedy selection. You in each iteration you do that selection, which is going to cover the maximum number of the nodes, which are having the minimum weight. Only thing is when I add this covered, what are the nodes that are covered? I don't add, if let's say A, B, C, D is there, A itself is not marked as the covered by default. So in the previous case, so the node A is also marked as the covered, and then when I do these subsequent selection, I don't involve that node A as a criteria to the selection. So, but that is not done here. So if you run that, make that minimal change and run it, you again get the some set of the probes, and then you output that as the thing. So just to give a simple example, here is the graph. This is a node weight graph. So the node N7 and N2 are the two probe stations in the graph, and then if you run the algorithm 4, so you will have one probe going from node N2 to N7 and from N7 to N2, because that is the mandate. And then the other two selections, one node from N2 to N6 to N5 and N2 to N1 to N3 to N4. This is the other selection that is done. So, but on the other hand, if you run the basic, the first algorithm greedy selection, so it will generate 3 probes at the cost of this one. So this is obvious. With the additional number of the probes introduced in the network, the cost is going to increase, but that will give you tolerance. There is some literature, it's not what if I want not necessarily only one probe station, but I want more than one. So I can tolerate up to 2 link failures, 3 link failure. Then what is the characteristics of the nodes? Whether they should have, the degree of those nodes should be, each of the nodes should have this degree or connectivity. Along those lines, there are some constraints. There is some literature that you can enforce those constraints also, and then build tolerance models. So what this diagram is showing, this algorithm is doing a simple fault tolerance model with one probe station failure. And again, we looked at some of the properties. If I introduce this additional criteria, what is the additional number of the probes that get added to the list? So this turns out to be whatever the number of the probe stations you have, half of them. So these are the pairs A, B, C, D, and then D, C, B, A. This is one pair, half of that. So every alternative the probe stations, that's the maximum, can probe each to each other. So ABCD and DCBA, and another PQRS, and the other way around. So like that. And second question that we answered is, if a probe station fails in the network, then how do we actually deal with that? It turns out that if you increase whatever the K that I selected initially, if you double that value of the K, so initially I start maybe 4 or 5 hop probe selection, and then if I increase that by, then you should be able to meet that criteria. What is that? Every node should be probed by at least one probe station. Why this must be true? So I'll just give an intuitive idea. So if let's say PJ is one of the probe station, PI is another probe station, any node which is from the probe station PJ, which is at the length K plus 1, should have been probed by another probe station. By instance, that should also be within the length K. That also means that some other probe station PK is actually probing that node. The distance between PK and that node is actually at the max, it can be K. So and then if that probe station fails, then by increasing this, all that can happen is, so this whatever the up to length K from PZ it is going, and then you extend that to another K length, then you should be able to reach the at the other node, up to that node. So I'll just, if you think of this linear chain, so A, B, C, D, E, F, G. So at the one end, maybe A is a probe station and then G is a probe station. So from G to the left-hand side, this is probed by the probe station G. And from A to the right-hand side, this is probed by probe station A. So anyway, if A fails, then all that you need to do is to, from G, you need to extend the probe length to up to the K, and then you should be able to reach the up to length of the node B. So that is the maximum, but it's that not necessarily it should happen. So if the length of the probe is smaller, or there are alternative paths from other probe stations, then you should be able to that. But that is the in the worst case, we may need to increase the probe length by twice of the K. So we also again ran this experiment on the same Rocketfuel experiment graphs. So these are large scale graphs. So in the autonomous system number, the number of the nodes adjusts the number of the probe stations that we selected in that graph by keeping the number of the hops, the probe length to be 4, and the number of candidate probes and the total cost of the selection. So compared to the previous experiment, what we noticed is in terms of the cost is not substantially increasing, and even the number of the probes also not substantially increasing. Why this is so? Because when I make the selection, let's say from probe station P1 to other node, some other node Bj, if I'm going, if it is already passing through the node, another probe station Aj, then you don't need to add another specific probe station to probe the other probe station. So even by definition, any selection that goes via that node will also cover that node also. So that is what we noticed. And to conclude, we selected, propose a couple of greedy algorithms to do the probe selection in the graph, which are reactive to the traffic dynamics in the network. And these algorithms are obviously faster than the optimal selection that you can do, but they are slightly suboptimal in terms of the cost. And we did some experiments with the simulations and the real graphs. We do have some measurement studies done in the internet, but in this talk, I haven't shown those diagrams. Precisely the question that one of the students asked, how do we actually change those probes? How frequently do we need to change? Those questions are also answered. So we are exploring currently, can these probe stations be dynamically relocated? So if let's say node Pi is the probe station currently, can we go in 100 node graph, if let's say I have 5 probe stations, if one of the probe station fails, can we dynamically instantiate and bring another probe station in the network so that the probing work can continue without the work being delegated to the other remaining probe stations? And so do want to do some experiments on data center networks. And the other theoretical question that one answer, can we select the probes which are completely disjoint in the there are no overlaps, meaning let's say I go from A to D, A, B, C, D, and there is another probe station so at E. So E to D and D to C, and then it is going to some other node P. So in this space, the path between C to D, the two different probe stations are actually going through that path between C to D. Can we avoid such overlaps in the final selection? So those are the kind of questions that we are currently exploring. So that is the way. So let me stop at this point of time with the thank to the organizers. So if the audience have any other questions, then I'd be happy to take them.
Hi, I have a query. Hi, Professor.
Yeah.
Have you do you have any plans to try your algorithm on an emulation framework or an actual testbed or server?
Okay, so test bed in a sense, what kind of a test bed?
Like for an example, a Mininet framework with something of a small scale Mininet network or OmniNet.
Okay.
Because
No,
yeah, tell me.
We haven't done that so far. We did some measurement study by picking some web servers and then sending the ping queries to them over a longer period and measured the RTT, how the variation of that RTT over a period of time. That study we did. But
You're talking about the Rocketfuel project, right?
No, not Rocketfuel Experiment. These are the custom probes that we sent from our lab computers to some of the popular web servers that we picked.
Okay. If it's okay, can you name any one of them so that?
Yeah, YouTube and Facebook.
Okay.
These web
Those
servers, those kind of servers. So we actually, even by running the traceroute commands, we actually found out what is the path that is taken by the
got it.
Yeah.
Okay, good.